here's a stupidly complicated proof for the Pythagorean theorem. First, we need to use complex numbers. So accept z1 plus equals z2. Z is a complex number. The imaginary part of z1 is equal to the imaginary part of z2. Same goes for the real part. Next, we need Euler's identity, or Euler's formula, which is e to the I theta plus is equal to cosine theta plus I sine theta. So to begin the proof, take e to the theta plus is equal to cosine theta plus I sine theta, and e to the phi is equal to cosine phi plus I sine phi. That makes e to the theta times e to the I theta plus times e to the I phi is equal to cosine theta plus I sine theta times cosine theta cosine phi plus I sine phi. Now you have e to the I theta plus phi is equal to cosine theta plus I sine phi times cosine phi plus I sine phi, or cosine theta plus I sine theta times cosine phi plus I sine phi, which is equal to, now remember Euler's formula up here, this would be also equal to cosine in theta plus I sine phi, or cosine theta plus phi plus I sine theta plus phi. Next up, so yeah, take that is equal to this. Once we distribute that out, it's equal to cosine theta cosine phi plus I cosine theta sine phi plus I sine phi cosine I sine theta cosine phi minus cosine theta cosine phi. Well, that should be sine theta sine phi. So cosine theta plus phi plus I sine theta plus phi is equal to cosine theta cosine phi minus sine theta sine phi plus I times the quantity is sine theta sine phi plus cosine theta sine theta cosine phi plus cosine theta sine phi. Now recall this, since these two things are equal, their imaginary and real components must also be equal, meaning cosine theta plus phi is equal to cosine theta cosine phi minus sine theta sine phi, and sine theta plus phi is equal to sine theta cosine phi plus cosine theta plus sine phi. But we should only need this. So let's set phi equal to negative theta. So you have cosine in theta minus phi is equal to cosine theta cosine negative theta minus sine theta sine negative theta. Now using even odd properties, we have cosine negative theta is equal to cosine theta, and sine negative theta is equal to negative sine theta, and cosine 0 is equal to 1. So you have 1 equal to cosine theta plus I sine theta, which is cosine squared theta plus sine squared theta is equal to 1, which is Pythagorean identity. Now take a triangle with angle theta and side lengths A, B, and C. Cosine theta is defined to be A over C. Sine theta is defined to be B over C. Now plugging that into this, we get A over B squared plus A over C squared plus B over C squared is equal to 1. So A squared over C squared plus B squared over C squared is equal to 1. A squared plus B squared equals, that should be a C squared. Now, let's look at Euler's formula. E to the I theta is equal to cosine theta plus I sine theta. Take a complex number A plus BI, with components A and B at angle theta. You have A is equal to cosine theta, B is equal to sine theta along the unit circle. So up here should be I. That makes A plus BI equal to cosine theta plus I sine theta, meaning Z is, let's set this equal to Z, so Z equals cosine theta plus I sine theta. That makes dZ d theta equal to negative sine theta plus I cosine theta, which is equal to sine I squared sine theta plus I cosine theta. Factor out one of the i's, so you have dZ d theta is equal to I cosine theta plus I sine theta, which means dz is equal to I times dz d theta is equal to iz. Now let's solve this differential equation. dz over z is equal to I d theta. Integrate both sides. You have the natural log of z is equal to theta plus c. The absolute value of c is equal to e to the I theta plus c. Absolute value of z is equal to e to the I theta, making z equals to r e to the I theta. Now let's plug in theta equals 0. We get z equals r. Do the same thing over here. Cosine 0 plus I sine 0 is equal to 1, meaning r is equal to 1. E to the I theta is equal to cosine theta plus I sine theta. Euler's formula. More. Let's look at the derivative of sine theta. It's the limit as h goes to 0 of sine theta plus h minus sine theta all over h. Using the properties we proved earlier, we can expand it to be all this. Sine theta cosine h plus sine theta sine h cosine theta minus sine theta all over h. Rearranging, limit as h goes to 0, sine theta cosine theta minus 1, or cosine h minus 1 over h plus cosine theta sine h over h. Apply the limit. You have sine theta times 0 minus cosine theta times, or plus cosine theta times 1, making the derivative of sine theta with respect to theta equal to cosine theta. Now let's look at cosine theta. Plugging into the limit definition, cosine theta plus h minus cosine theta all over h. Cosine applying the formula we proved earlier, where you get cosine theta cosine h minus sine theta sine h minus cosine theta all over h. It's cosine theta times cosine h minus 1 over h minus sine theta sine h over h. Cosine theta times 0, sine theta times 1. The derivative of cosine theta is equal to negative sine theta. So do you see the problem with here? If we go back and look at the proof for this, we used Euler's identity. The proof for the sum difference formulas, they're somewhere in here. Here, these, we had to use Euler's identity, or Euler's formula. But to prove Euler's formula, we had to use the sum difference formulas, meaning this proof for the Pythagorean theorem using only trigonometry and complex numbers is self-referential. Fuck.